the future. Now, when we start getting into the whole idea of what is a resource, you hear the politicians talking about these terms a lot. You hear the term resource and you hear the term reserve. And these are two distinct things. We're going to see that the concept of a resource, which you hear a lot from politicians, what a resource we see is typically a naturally occurring substance, and in some cases actually human-made, but it somehow has to come from something. So usually it's a naturally occurring substance of use that could potentially be exploited by us using current technology. So literally anything on the earth is a resource. Rocks are a resource. Fire's a resource. Trees are a resource. The soil's a resource. All these things. So this is just theoretically things that we can use, and stuff that we can't use is obviously not a resource. And what's neat about the way we work is that resources, things that are not resources today can become resources in the future. Like, for example, petrol at one time was not a resource at all, had very little human use, and then became used for other things. Now, you also hear the term reserve. And this is a very politically heated one, because these are resources that are economically exploited. That means we have the ability to use them now. They're economic to extract or to obtain, and we're going to see this is very important looking at the history of resources, and basically, they're discovered. Because this sounds kind of silly because some resources are not yet discovered. And we hedge our bets on these sometimes, that we have this future where we will be able to tap into other things. And that literally means sometimes other planets. We have undiscovered resources. Also on our own planet, we find that we hypothesize about undiscovered oil deposits and diamond deposits and whatever. And we see that there are potentials for oil, more oil off the Gulf of Mexico, and we just had an undiscovered oil reserve that was hypothesized but then discovered over Brazil, which is now being tapped into. And in Alaska, we have, northern Alaska particularly, probably undiscovered reserves of diamonds and coal and other things. So a reserve means that it's available. And when we start tapping into what we call reserves, that means that stuff that we have stored away typically, that we keep, so we have this resource available. And typically resources are obviously smaller than, reserves are smaller than resources. And reserves change as technology advances, the levels do. So we might have a reserve that's being used quickly, and then all of a sudden another technology becomes a resource, or another energy source becomes a resource, and that reserve now remains as it is intact. Now when we look at resources or reserves, because again, a reserve is a subset of a resource, we can generally categorize them into what are called non-renewable and renewable. And these are kind of not arbitrary categories, but they're based on time and convenience. Because non-renewable energy basically means those resources or reserves that are being used faster than can be replenished. It doesn't mean they cannot be replenished. For example, coal, oil, and natural gas can be replenished, but it takes a lot of time to do it. And in some cases, the resources that we have now for coal, oil, and natural gas, it takes 100 million years for them to form. So obviously, we can use it up quicker than they can reform, and they end up being zero. Now, renewable basically means that we can replenish them within a convenient time. And this is not always feasible. Sometimes it could be very costly, and it's not always practical. We're going to look at solar, geothermal, tidal, and other sources of energy that are renewable, but are they comparable to what we're doing today? Because we're going to see that as far as energy goes, our history is stuck in what's called this turbine and lever type of history. That means we have two major machines that we have used throughout history that have guided us and dominated us. And particularly the turbine, which is also called the motor, okay, is a major way of getting around, transportation, a major way of manufacturing and producing electricity. So like 99% of our energy, is associated with some type of turbine or rotor, and that limits us in how we think about the future, particularly with these technologies here, these alternatives right here. So when we look at the history of energy, and you're going to see a short video on that, is when we look at how we run technology, because today energy runs technology, or it maintains our technology. And in the old days, I mean the old ancient days, okay, we started seeing human labor power. And that labor power is either as a hunter or a gatherer or an early agriculturalist, as we see even occurring in many countries today. So this gave us the term actually manpower, which does not mean man as human, but manus, which means hand. So this was power done by a human hand, whether it be male, female, adult, or child. And then that slowly moved, once we became agricultural and tamed animals, to this whole idea of animal labor. And then you hear the term called horsepower, because cow power or bull power or ox power sounds pretty funny. And horses became the standard, particularly for transportation and for draft purposes. That means pulling a plow. Horses were more tameable than other animals, which is why they became the standard animal of labor, and including donkeys or asses too, what we call them. So whatever. So we see these units today because they were the major comparison for us to adapt to other technologies and other energy sources. So if, let's say, the first petrol engine, which ran the first car or truck or bus, if it did not meet animal labor, the horsepower unit, which was measured by, it was impractical, and it was not a resource at the time. So when we look at, the energy of using something as an energy source, that means another type of resource besides human labor and animal, what we look at mostly is combustion energy. That means using fire. That was the next thing that was tamed by people, using fire to do things for us. And that included cooking food, which turned out to be a very good thing. It reduced food poisoning and actually made food more digestible, believe it or not. Heating our living areas made us able to live up north and survive winter climates without too much death. And most importantly, it helped us to build technologies that later on we could exploit other resources from, particularly energy resources. So it gave us the ability to forge metal, particularly the harder metals like steel, which gold and silver, you don't need the metallurgy as much. Okay, it's easy to extract and it's easy to mold by hand. When we start looking at steel in particular, okay, heat became a big issue. And energy, particularly in rapidly growing settlements, became a big issue because as civilizations formed, cities grew, the energy needs in that area grew sometimes beyond the capacity to provide people with that resource or with the reserves. So when we look at the first source of energy, wood was one of the primary sources of energy that built society as we see it today. And wood ran machines. Wood in some days ran even car engines. That was hypothesized at one time. Wood ran the trains. It was used for construction material too. It had an incredible purpose. And so again, it fueled the Industrial Revolution and led up to it. It led up to metallurgy, where you can produce enough heat to at least work with some of the soft metals. So wood fueled us and fueled civilization to grow. And this is what led to the searching for more energy sources and more viable energy sources. So wood was an incredible resource. That was a limited resource until we learned we can produce energy and run things with it. And as a reserve, it started disappearing. And in some countries, it's almost gone. They just totally stripped forests of wood, particularly for energy use, for cooking and things like that, which is still done today. And we're finding out that wood is not a disappearing reserve as much anymore because it's been replaced by other energy sources that we use to cook, heat, and run machines. So when we look at what wood has led us to, literally 100 years after the Industrial Revolution, we really didn't change too much from the 1600s on to about the 1850s. Wood was still a major energy source, and we tamed wood enough and were able to actually turn wood into charcoal, learning that by compressing it and drying it, it burned hotter and longer. We were able to start building better machinery and furnaces and stuff like this. And this, by time of the early 1900s, okay, started giving us now the ability to dig up coal, because coal required a lot of energy to dig out, not just human labor, which coal even today uses human labor, but also to move it, for transportation, to build machineries to run the mines, so and to dig the mines. So coal became very popular and represented a large portion of energy usage. Now also notice this, and this is actually petrol. That means liquid petrol, which, believe me, comes out of the ground as a thick, gooey, dangerous substance that in ancient history, right about here, going all the way back in time, the only purpose it served was as tar, and for basically, you would attach it to, you would rub a cloth or a stick in tar and use it to burn as what's called a soot lamp. Very stinky, but it produced light. It wasn't good at producing heat. Petrol was actually useless. But right around the coal period, coal burns much hotter than biomass. And that gave us ability to work with better metals, build more elaborate machines, and also have the energy to exploit petrol. So we were able to make bigger machines and discovered that we can make machines now that can actually drill for oil. And we also learned that coal can be used to break apart oil into its various components. We call this cracking and distillation, because today when they get petrol out of the ground, it is turned into at least 20 primary products and then hundreds of secondary products after that. That includes everything from plastics to nylon to jet fuel to whatever. So petrol is a very versatile thing, and understand that it was not really used a lot until around the 1970s, from the 50s to the 70s, when this peak came with the growth of the carbon automobile. That means automobiles were literally in everybody's hand, and we had the suburbanization of America and the building of incredible highways. And it's also true in other parts of the world too, as we moved from public transportation to cars, and cars got more affordable worldwide right around 1970. And from there, we saw also a slight increase in natural gas, because natural gas at one time was a waste product. We sometimes use it as cooking gas, and now we find out that natural gas has a heat capacity under the right conditions that we could use it as an alternative in many places to oil. And we could use, so we use it still for many specific purposes, but it's great for cooking, which replaced coal, which was stinky and dirty, and wood, which was, again, stinky and dirty. And believe me, at one time we burned cow poop too, and people still do that. But natural gas has a very much higher BTU than any of these when used for cooking, and it's also cleaner. I mean, you can't see the pollution from it, which can kill you, but it doesn't soot up the house. So this started becoming called clean cooking gas and clean cooking fuel, and was also used eventually to heat furnaces in houses, which at one time oil and coal used. In the house I grew up that I was in high school, when I was in Brooklyn, was a 120-something-year-old house that had an oil furnace in it still, and we had to have a petrol truck come in, to put in heating oil. And eventually, I know the owners, the people that bought the house, turned it into natural gas because it was safer and cheaper. And we see here, as you get towards the top, hydroelectric has always been a power source with the generation of electricity. I mean, it's been a power source in general for running machines, but to produce electricity, obviously, that didn't come about till we learned how to turn it, till Edison and Tesla developed their motors for producing electricity. So once we learned that, water can turn with enough power to produce electricity, this became exploited, but pretty much stayed pretty stable, because petrol and natural gas were doing a darn good job for us and seemed abundant. And the nuclear also did too, but nuclear is kind of stabilized. And we still see it kind of like at this point, including hydroelectric, and we'll look at those a little later. And renewables, which hydroelectric is kind of renewable, but water supplies can divert. And nuclear, there's a lot of natural nuclear materials out there, and it is recyclable, but we still could use it faster than, we can make it or excavate it, and recycle it. So these other renewables, which we'll talk about, have always had a small presence because they're still kind of like in that non-reserve phase. That means they're still not practicable or cost effective to do. And we still see that they need incentives in order to be profitable in various situations, which means they're not economically feasible. Now, your book goes into the role of the automobile. And again, it wasn't until around the 1940s or 50s that automobiles really became popular, not only in the US, but globally. And this permitted us to basically speed up the growth of cities, to spread ourselves out, to build more types of transportation, but really allowed us in general to drive more and to get around more, because cars particularly became more convenient and they became more efficient. So they played a very big development in industrialization. Plus the petrol truck in general and petrol trains allowed us to transport incredible distances. So what we saw is a spread of America and its increase in the needs to produce and collect resources. It gave us more access to resources and reserves, and it also allowed us to literally shrink the earth. But that means at the same time being able to transport stuff from incredible distances and very quickly, unlike what we saw with ship transportation and literally foot transportation like what occurred in the Silk Road from China to Europe. So how is energy used? Okay, we're going to see that energy usage differs greatly from the developed countries. What I mean by the developed countries is not we're socially developed, but literally technologically developed as far as amount of technology per person, per capita, compared to China and other countries that tend to have less technology per person. So it has nothing to do with social development, intellectual development, or how far along they're advanced in their technology. It has to do with the per capita technology. We use much more than China, and much more than we see in people in other countries. And this is why we can criticize them when they do use technology and they do pollute, because we are greater users by far. And this is something we have to keep in mind all the time as we get to this 2050 scenario, very much like what Hans Rosling was saying. He says, we better start looking, particularly we, not so much them, but we got to start looking at alternatives to reduce our 3 to 5 times more usage in China, because that's about, an average of that, to the 16-fold almost that we see with people in developing nations. Remember, guys, this makes up about 80 to 90% of the world's population. This makes up about 10 to 20. So 10 to 20% of the world's population is using most of the energy. And we're the ones that have set an example for using less, and not just for them to have, but for us to have in the future. And don't forget, we're going to see that a lot of these countries are what we buy that energy from. And they don't have to sell it to us if they can use it for their own economic development. So when we look at energy consumption per capita in general, man, we can see some distinctions here. And I want you to look at this in your book and in your PowerPoint. Whoops, the Canadians are slipping here, but they have a reason to. They spend a lot of money heating. I mean, because you see this for Alaska too, which, they help, the northern states help to elevate us. But Canada spends a lot in lighting and in heating because of their environmental conditions. But look at America. On average, and we have a lot of climate that does not need that much energy, because a lot of this is coming from electricity and cars and probably unnecessary things. So we see us here, we see Australia, and we see Europe, which Europe, tends to be less energy users, mostly because of, capacity and also just lifestyle. And then we look at here, like developing countries, and especially Bangladesh, which has very little technology per capita. So this is this disparity that we see when we look at the world, very energy intensive, using up resources that are not even on our property, that are in these people's areas. That means we use their resources, sometimes as a source of energy or material goods for our energy uses. And again, here's another chart. You see lots of charts. I love charts. This one looks like a New York City subway map, but it basically shows us the uses of energy. So when we look at here, when we look at electricity, which is one of the most common ways, transportation, electricity, I guarantee you'll see it in a test, are the two major uses of energy sources, particularly fossil fuels and things like that. So we can see for us, electricity is produced by coal, a lot of it. Produced by natural gas, and this tends to be more local. This tends to be more, large amount because of the heat capacity. We can see a little by wind, a little by hydro, a fair amount by nuclear, very little by solar, because solar is used for other things, but for electricity right now, it's not 100% feasible. And then we can see that, energy goes into other uses too, like manufacturing and other things. So when we look at energy sources in the United States, we have a variety of them. Matter of fact, we use all of them, but in different proportions. And a lot of this is due to that our machinery heavily relies on natural gas, coal, and petrol to do this. There's petrol right there, particularly for transportation and for also sometimes electricity production, very little. You actually don't see it leading to electricity production except a very small amount. So this is how we use it. And I think this is very important to keep in mind because, again, we use a lot per capita as people. Okay, this is showing transportation uses of energy. So we're not looking at electricity, we're looking at transportation now. And we can see here's where the United States leads. So Canada uses theirs for heating and cooling, electricity. We use cars as a way of eating up a lot of petrol. And they're a little more conservative about it. Australia, there's Europe again, they're in their own little world. And same here where we see, like Hans Rosling was mentioning, we see people that are animal and foot power and bike power here a lot, okay, and sometimes moped power or small motorbikes, which are still, they get 90 miles on a gallon, 100 miles on a gallon. They're not a big issue. And then we start getting more into cars and, again, motorcycles. So this is incredible. Again, when we look at resource usage, this is for transportation, particularly the personal car. And I'd hazard a guess that the personal car probably makes up about 60–75% of this usage, which is a waste because we can put that into trains, public transportation, and other things rather than just individual cars, and particularly public transportation because we don't make use of it enough. We don't make use of our long distance transportation like railroads. So now let's take a look at electrical energy. Electrical energy eats up, in our country, a lot of coal. I mean, this is true in any developed country. It's mostly coal-based, little water-based, some natural gas-based. Natural gas tends to be more local, okay, and more, household than anything else. But man, this is a great consumer. We are electrical energy gluts. And you can see here, when we look at fossil fuels, how much in various countries they use fossil fuels. Look at Japan, India. I mean, this is where the United States is not as guilty. Okay, when we start looking at coal, particularly as a source, Japan are coal hounds. They use very little hydroelectric because they don't have that much. They have some renewable. They have some nuclear. Nuclear is a hazard in general, and there it is, but very little. You look at France, and this I've learned from traveling through Europe in general, but particularly taking the Eurail trains through France to get about, Europe. Man, those trains, it is like going through nuclear power plant heaven. But they have no other resources. They don't have petrol. And they prefer not to buy petrol from the countries that they have to buy it to. They don't want to deal with them. So they rely heavily on nuclear. And so far, there hasn't been major catastrophes. We'll learn that nuclear can be safe. It can be a good resource for us, actually a good reserve for us. Look at Norway. Most of their energy is from hydro, but they can do it. And the same is true for Iceland. They can do it. And they also use some thermal energy too, Iceland more than any other country, and also Denmark, because they have natural volcanic areas that produce steam. We'll see how this works. So with electricity, we're still very carbon based. That means fossil fuels, particularly coal. And coal is, not only used to make electricity, there's a competing factor of coal to produce petroleum. It's one of the major constituents of heating the units for making petroleum. Now, when we start looking at development of the world, there's always been a lot of elitism about why development occurred in Europe and in parts of China and the Americas, and not so much in, let me point those out, in these countries here. This development was imported from Europe. This development too, parts down here, were imported from Europe. But when we see no development here, particularly in India, a lot of Southeast Asia, not so much, parts where you see the black. This is where fossil fuels are found. Okay, particularly the fossil fuel called coal. Coal is what drove the Industrial Revolution. Coal allowed us to build incredible machinery that can burn real hot, that can make steel foundations, that can forge things beyond belief. Coal was an incredible energy source, but look, it's missing in the countries that did not build large cities. That's because they couldn't. They had only soft materials available. They also did not have the ability to exploit a resource they were sitting on. And when you look at this map and compare it to this, look at petrol. Petrol is found in the areas where we don't see that these huge cities forming. Now they are, because they've been invaded, basically taken over, inhabited, or colonized, whatever you want to call it. And also they've been giving the machinery to tap into their petroleum, which at one time they never even knew was there and didn't care about. It was not even a resource. So this is kind of neat when we look at this, on how where petrol is, development didn't occur until later because coal is what drove us. So this is the discrepancy between coal and petrol. We have a fair amount of coal, which is why we can still use it to produce electricity. They don't. Okay, a lot of this doesn't. And they have to use natural gas or other means. So we see some parts of the world here still don't have electricity. The United Nations is trying to get electricity in these areas, but petrol is a bad way to do it, and burning wood is a bad way to do it, and they don't have access to coal because the coal's here. And we won't sell it to them because they need it, and if they have to buy it, it's expensive. And they could buy coal from these little regions up here, which are, Europe, where you see right here, particularly, Ireland. Okay, so this is neat when we look at this, is the resources are kind of polar distributed. That means petrol's in one place, coal's in another. This drives a certain type of development. This drove early development and allowed us to exploit this resource. Now, when we look at coal, what do we do with it? We burn it. And guys, there's no such thing as just coal. There's several types of coal. There's what's called peat coal. It's literally old swampy areas that the grasses and reeds and cattails and stuff and swamp creatures died off. They became compressed and they rot. Peat, its major purpose, it's a very wet, burning material. It's great for steaming stuff. It's great for low intensity fires. You can cook with it, but it's not great. As we look on, is on certain areas, these peat deposits that came from ancient swamps, okay, became compressed over time by soil overlay and by what are called metamorphic processes, geological processes. Is peat becomes what's called lignite. Lignite is sometimes called soft or wet coal, and this is a great coal for fires. It's very much like charcoal. It's a steamy type coal. You can use it producing steam, okay, but also producing heat, in the form of a fire. And then as we get drier and more compressed, we get what's called subbituminous coal. So bituminous coal, we'll see, has its own purposes. And the same is true for bituminous, which is drier. Then you get in what are called the anthracite coals. This actually looks like solid glassy rock. It's beautiful, dark. It takes a lot to burn it. If you ever sometimes try to burn charcoal and it won't start, that's like trying to burn subbituminous. It takes a lot of fire to burn these three. Not much to burn them, but they don't burn hot. This burns incredibly hot, to the point where you get it so hot it can melt a lot of metals. But it takes a lot to do it, a lot of energy input. Now, so coal, of all our resources that we burn, fossil fuels is the most abundant fossil fuel. The problem is we have no way to make it. I mean, we can kind of from like making charcoal. But we here again have lignite. You can see the properties of, and this is something to look up in your book. You can look up the purposes of subbituminous coal and bituminous coal, which again is used a lot. This is what's used in power plants. This is what makes most of your electricity. And it's widely used because it's the easiest to get at, and also it burns pretty well. And then anthracite has very, very specialized uses, because it's usually used for heating buildings. I mean, it takes a lot to heat it, but once it burns for a good long period of time and produces a lot of nice dry heat. Okay, that is perfect for a lot of the furnaces. And I remember in elementary school being given the privilege sometimes of going down to the furnace room and seeing this big, hot, massive anthracite coal burning furnace and the poor little guy that ran it. So coal was not always a resource, basically, because we didn't know it was there. And when we did find it, we didn't know much to do with it. And now it's a well-known reserve that is economically feasible, again, to get out of the ground. And this is a typical mining operation. There's different types of mines. There's hillside mining, in which they just basically go into a mountain, drill in, and do a shaft. There's also deep well mining, which you have to actually dig down and produce a tunnel under the ground. And there's variations of all of these. So we have what are called drift mines and slope mines and vertical shafts. But usually what these are, again, are ancient swamps that got covered over or moved about by plate tectonic activities. So it's what we call a sedimentary to metamorphic material. And it does take a lot of environmental damage to do this. And I've seen, even in Illinois, when I was living in southern Illinois, houses that were over these shafts sometimes would collapse and fall into the ground and sink. So it does produce a lot of damage to ourselves too, our living areas. Now let's compare this to petrol, coal to petrol. Petrol is more of an oceanic formation formed by rock. So they say petrol comes from dinosaurs. That's not necessarily true, probably more coal than anything else. But yes, dinosaurs are found in these areas where oceans basically covered up the dinosaurs. So this is usually oceanic. And usually when you look at an oil formation, it is layers of soil that formed over an ancient ocean, usually a saltwater bed. And this is where you get this term salt domes, sometimes you hear in Texas. It's a dome of rock or salt that covers up the oil. So you have what are called clay domes and salt domes and things like that. Clay domes tend to be a little more inland, and salt domes tend to be more coastal or sometimes underneath the ocean in what we call sea drilling or offshore drilling. But what a petrol reserve is, it's just like coal. It's rotted plants, particularly algae, a lot of sea animals whose bodies decayed into a liquid we call petrol. And also they're further broken down by microbes into natural gas. It takes microbes to make it. That's why we can actually make natural gas. Excuse me, we can have micro make it. So these deposits are very ancient. Again, like coal, they're very ancient. They take special conditions to occur, and they're very limited. And we know that they're not that common. They're very geospecific, and probably there are other areas that are deep down in the earth that have been covered up by plate tectonics or other activities that we still explore and try to find. Now, when we extract petrol, this is unlike coal. This is just kind of like a drill and then we don't suck it up. That doesn't work too well. What we do is we actually push it out by using the pressure of injecting water or cracking the rock, like in the case of fracking. That's what it means. It means fracturing the rock. We can pour hot air down there. We can pour polymers down there of sugars, very much like slime. But our goal is to push the natural gas and the oil out of that well, because it just kind of sits there, floating, held in place by this cap rock or by this salt dome. And always there's going to be natural gas there. All an offshore rig is, and they have deep offshore versus shallow. It all depends on the ocean bottom. But these are just doing the same thing. But instead of them setting up on land, these have to be kind of floated, suspended, and then they drill into the soil above that area. And guys, one thing about oil spills, and I saw this actually on research ships that I've worked on when we were scanning the bottom of the ocean. Natural gas leaks occur. I've seen bubbling coming out of a coral reef that was actually natural gas when they detected it. And there are cracks in the ocean floor, very much like getting a crack right here, because just imagine deep, offshore drilling is this with water on top of it. This will crack as, the salt cracks, the earth shakes, whatever, plate tectonics, land moves, and you get natural oil spills. And this sometimes makes it difficult to determine. Now, each source of oil has its own chemistry that makes it unique. So if we find an oil spill here, and that oil spill is typical of the chemistry of oil, let's say from Saudi Arabia, then we know it's a leak. If it's more typical of, let's say, the Gulf Coast, and this is the Gulf Coast, then we know that could be a natural spill. And today, when they drill petrol, like this facility here, they actually label it with a chemical signature and sometimes even DNA, so they can detect where that oil came from. And that's kind of neat, but that's to make sure that the oil does not contaminate the environment. And if it does, we find out who's responsible and who's going to pay for it. So again, when we look at fossil fuels, since their discovery, we've relied on them heavily. And our infrastructure, that means how we built our society, particularly this thing called the turbine or the motor, okay, is that it is the feature that we are kind of stuck with in no matter how we design energy sources, but they're particularly adapted to fossil fuels. That means wood in the old days, today more coal and petrol or natural gas. So this is our habit, and this is a very hard habit to shake as a society. So what are alternatives? Guys, since we're a turbine society, all we need to turn a turbine is heat. And there are lots of heat sources, and we can burn human bodies if we dry them and want to. And that's actually been done. We won't talk about that. We don't know if that's urban legend or not. At one time, people were burning mummies. There was a whole spate of, bunch of mummies at one time coming out of Egypt that were common people. That was done at one time. And supposedly people tried to burn them in a fireplace or as a source of energy, machinery. But nuclear is probably our next growth area. We see that Europe has been using it successfully without any incident. Russia, sorry about that, obviously is, Japan is, and we're moving in that direction. United States sits on an incredible amount of natural uranium. And this is what puts us in a good position for it. Other countries don't have that luck. So usually nuclear is exploited where you can get uranium from your own area or cheaply from someone else. It's actually mined out of the ground. And there's a lot of uranium mines actually right around College Station area to heading out south west past Austin, San Antonio area. It's natural. I mean, it's Nevada, Great Plains has a lot of it. It's a naturally occurring rock. Okay, so it is a resource that we know is also a reserve. That means it's feasible, it's doable, and the only reason why we don't build a lot of it is because of public sentiment and the fear of it. And also they're very expensive to set up, and they have to have a payoff. Because why change over to it when petrol's still cheap and you have to wait for a long-term payoff to use nuclear? So we're going to see I want you to read about this. When we look at nuclear power, guys, we're looking at harnessing radioactivity. And there's and radioactivity basically is looking at unstable atoms that break apart. And whenever an atom breaks apart, it gives us various sources of energy, including intense heat. Now, the intense heat is not a problem, except when you're near an atomic bomb. That could literally incinerate anything and turn literally soil into cement. I mean, actually into glass, and return you into nothing but a puff of smoke. So unlike a nuclear bomb, we tend to contain that energy in what's called a nuclear reactor. So really, when you talk about atomic bombs, it's not the radiation, it's the heat and that hot wind, that impact that does it. So besides heat, a lot of it, we get off things called alpha particles. I would not worry about them. They can be stopped by a piece of paper, and your skin actually stops them from entering your body. Very minimally radioactive. We don't really do much with it. We don't put it to work. Beta radiation, this could be put to work. We could use this, and beta radiation is used in various processes and medical imaging and stuff like this. But it can't be stopped very easily. It can pass through clothing, glass, and aluminum, and you have to wear special suits to protect you from it. This can damage your cells. What's really the most damage is what's called gamma. And this is where you get into things like x-rays and the scanners you see at the airports. This is actually a form of what's called electromagnetic radiation. It's related to light, but a very bad light, again, very similar to x-rays. It's very high energy. Alpha is very low energy. And this in itself can produce heat. It can produce destructive force against other atoms, and is very good at tearing apart our molecular structure, particularly damaging DNA. And gamma radiation can pass through literally anything. It requires several feet worth thickness worth of brick, cement, and lead and metal in order to absorb it or slow it down or stop it. This is the most dangerous, obviously, of the radiations. And this is what really causes the cancer. But so does sometimes ultraviolet light when we think about it, from sunlight. And guys, gamma radiation comes naturally from soils too, from things called radon and other radioactive materials. So what drives a nuclear reactor is, again, what we're trying to do is produce steam. And the steam, for now, comes from a process called nuclear fission. There are what are called fusion reactions. And there's a lot of misconceptions of whether these are feasible or not, or doable. And if they are doable, can they produce heat? It's still in the stage of not being known. And we have these things called cold fusion particularly, which says that we can produce intense heat by playing around with atoms and putting in very little energy. But it's very unusual that we can put in little energy and get away a lot. Because even with a nuclear reactor, you're putting in a lot of energy and losing most of it in the production. You're not getting a one-on-one relationship here. So with nuclear fusion, what we do is we set up the conditions for particularly a radioactive isotope called uranium to literally become unstable and fall apart, which it is naturally. But what we do is we mix it closely with other uranium particles, and it explodes, one explodes, and provides the energy for others to explode literally within the same time. This is called a fission reaction. Now, if you can't control this, you end up with an intensive uncontrolled release, which makes a bomb. If you can control the spacing between them and the amount of force that this explosive material hits them with, you can contain the reaction. And that's what a nuclear reactor is all about. And we'll see a little animation of it and I'll lead you to a video about this. Cute little video. Now, the problem with a nuclear reaction is your uranium, no matter what type it is, there's 238, 235, it depends on the intensity of the reaction you want, it gets converted into other materials and ends up eventually, something we call plutonium, which is called low grade. Now, this is the problem. This could be also used in low-end reactors. It could be used in bombs and stuff like that. But this is a waste product, okay, that eventually itself decays over time to the point where the material is not radioactive. But it does end up becoming what's called a toxic heavy metal. These also produce byproduct atoms too, we're not going to worry about. So this gets used up. And in a reactor, what we have to pay attention to is how much percentage of this fuel is left so that we can produce enough electricity, literally enough heat, to get the job done. And guys, a typical nuclear reactor can probably run 20 to 50 years on a fuel cell. That is not true for a coal-fired electrical plant, which needs a constant influx of coal. They will run out probably within days if there's a coal shortage or a lack of coal. These plants, if you would abandon them, they can probably run themselves for 20 years, except they'd fall apart due to lack of maintenance. So it's incredible. And these are very popular in the military. When we look at nuclear subs, nuclear power ships. I mean, we've at one time people experimented with nuclear cars and trains, but the problem is the incidence of crashes makes that a little unfeasible. Except the core, the nuclear core itself is very durable. I mean, you have to do a lot to destroy it. Okay, usually it's human error that causes problems with these things. So now here's what your reactor looks like. And this is an area called 3 Mile Island, which is right near my mom on the Susquehanna River in Pennsylvania, in eastern Pennsylvania. So this is not the reactor. Those are the cooling areas, and these are far from the reactor itself. Right about here, what's called a condenser. That's where you see the cooling water. So that is just steam. That's not a puff of radioactive smoke. I mean, you can play in that. It's not going to kill you. The reactor is probably around here somewhere in literally a very small environment, mostly surrounded by a lot of stuff. And you'll see this in a video. I'm not going to go into too much, but you'll see this is where the heat comes from. So that's your heat source. And this is heat in a container of water that is kept under pressure and basically produces steam in this chamber. This is a newer reactor. Older reactors didn't look this complex and are actually pretty dangerous because you directly heated the water that was turning the turbine. This is indirect to keep this away from the reactor itself, because this is actually filled with water itself, you'll see. So there's your heat. You produce steam. This turns a turbine, very much like what coal does. Coal produces steam heat, turns a turbine. So can petrol, so can natural gas, so can wood. So we're turning a turbine, and thanks to Edison and Tesla and a whole bunch of other people involved in that, we can make a fancy motor. It's a fancy type of reverse turbine, which when we put electrical wires on it, produces what we call AC or DC current, and that current then goes to run the city. AC is used for long-term power transmission. DC is what runs in your house or local transmission. Now the problem is, after this turbine is turned, that steam has to be cooled to recycle the water through here. And this is where we get usually environmental water. That means through an ocean, lake, or a river. And notice this comes in. This is very hot, and that water comes out hot and can create a heat pollution environment into that body of water. So we usually try to pick very big rivers like the Susquehanna right there, which has multiple parts on it, actually a very big cold river actually, or oceans to do this. So we do have to have environmental water that keeps this system running. And guys, if it does heat up, if the water stops flowing, because sometimes these pipes get clogged by zebra mussels and stuff like that, and just corrosion, particularly with salt water, the system does have a fail-safe of shutting down. So this is a reactor, and again, you'll hear about more in a video. Now, what makes nuclear energy the big problem is when nuclear energy was first developed. And guys, reactors were coming online in the 1950s. I remember one growing up in New York that was around during the late 60s, early 70s, and they were called Hunts Point, New York. We used to go up there. There was a big picnic area there, which is kind of funny, right in the shadow of a nuclear power plant, but that was probably safer than the neighborhood I grew up in. So when we look at the nuclear fuel cycle, uranium is a fuel. It is mined. And in the form that it comes from, guys, I wouldn't lick it or roll around in it, but it's not going to kill you. People live in soils with that uranium in there. But these are usually concentrated pockets that we dig out of a mine. Okay, it gets transported to something called yellow cake. That's what it actually, I guess it looks like yellow cake. Okay, and then it's converted into actually a gas called uranium hexafluoride. That gas now is easy to contain, easy to ship, and it is enriched, which means basically it is concentrated and incorporated it into these things called fuel rods. They didn't show fuel rods on a previous diagram. They showed things called control rods, which is what controls the amount of radiation that is coming out of the fuel rods. So the fuel rods are the radioactive, what are called the hot part of it. That's what contains the uranium material, the uranium oxide. Okay, and other stuff is mixed in there. The fuel cells then, of course, go to reactor. They will last dozens of years, and then when they run low, not run out, when they can't produce enough heat and become inefficient, several things can happen to them. They go into waste storage, okay, which we have a shortage of, unfortunately, and I'll lead you to another video on looking at where do we store this stuff, okay, or it could be recycled as a spent rod and go back to the conversion process. That means they, just like they get the uranium out of here, they get the uranium out of here that's still in there and concentrate it and recycle it. Guys, each step of this process is protected by the federal government. I used to have a license for transporting radioactive materials in hazmat when I drove trucks as a kid, okay, to get through college. And I've made use of that license for a university when I had to haul radioactive material from Oklahoma Panhandle to Los Alamos, New Mexico. And man, there are strict regulations on that. And you're usually, particularly in the big trucks, are protected and watch, and you have only certain highways you can go on. So there has been errors in the past that have contaminated various parts of the United States and the world in the old days of doing this, but we're getting better. But this is where most of the pollution comes in, is really in the processing, not so much the operation of the units, but it's in the processing and transport of the uranium itself. So when we look at it, this is the safe thing, or the safer thing. Not saying that there's no dangers to it, but this is where we run into most of the problems with uranium getting into the environment. Now we're going to kind of finish up with renewables. And man, there's a lot of them, and eventually we'll find out there's more as time goes on and we get smarter. But man, this is going to be where we're looking in the future. That 2050 scenario, if we don't get off of fossil fuels and find renewables that replace or substitute for fossil fuels, we're in deep doo-doo. And doo-doo is a good fossil fuel. We'll learn about that when we look at water treatment. So what we're looking at mostly is re-exploiting biomass. That means going back to plant material that was used to form coal and wood in particular. We're looking at more exploitation of hydroelectric, because water power, guys, you can use water to directly run machinery, but it's a pain and it's limited, and that's why societies abandoned it. I mean, that's how bread was milled, and a lot of things were made in the pre and the post-industrial revolution, early into it. Solar panel power, we're going to see, produces various sources of energy. Wind energy, we're going to see, has its issues. Geothermal, which not too many people know about because we don't use it at all, I think, in this country. And then tidal power, which we'll see we're trying to find use of even in the Houston area. So when we look at world energy consumption and we look at what we use, we are still a society that's dependent on non-renewable. That's it. We're stuck with it. That's the way we work, and that's where infrastructure is, and that's where our economy is based. So when a politician starts screaming about going to away from non-renewables, man, that is affecting the big C word, coal, and the big P word, petroleum, which still is feasible and makes a lot of money. And that's a problem. And we tend to be stuck in a rut. The French don't make a lot of money over that. So they spend a lot of money to get that. So they're very good to get to a non-renewable, which, and again, when we look at uranium, it really is non-renewable, but seems to have the aspects right now of more of renewable. Okay, so this is the real big goal, is how do we exploit this to the same point that we can live this way without having that? So again, we're looking at probably the major contributors going to be biomass. And I hate to tell you this, but that means how do we replace non-renewable? How do we replace coal, petrol, natural gas, wood, and use it in a way that we can keep growing it at the rate we use it? Guys, that still produces CO2. that still produces greenhouse gases. So looking at biomass is not a way of eliminating pollution. That is junk if you hear that. It is a way of eliminating these. That means we won't run out of them and we won't have a Mad Max apocalyptic society, whatever. Hydroelectric is always going to have its place, but it's only going to be in places where it can be exploited or where we can change the terrain, like Hoover Dam. And in Canada, they do this. Niagara Falls had a natural one. I just got to see it. Both the power plant in Niagara Falls takes natural advantage of that waterfall. But that waterfall is shrinking and shifting around, and that's affecting the placement and the utility of that hydroelectric power. But we can build waterways that do it. Solar, wind, geothermal, you have to be in the right place. Some areas don't have much wind, or they have wind very sporadically. You go to Oklahoma, which, I used to be a professor up there. Man, it was windy all the time. And I remember the day it wasn't. Okay. And solar, again, you got to be in the right place. And it only works during the day when you have, sunlight. That's a problem. So when we look at biomass, I want you to read your book about this. Biomass, again, is just looking at fuel, optional fuels that we can replace and using alternate sources like corn to produce ethanol, looking at algae and other things and poop to actually produce methane and using them to make petrol type compounds. We have an algae now that can actually produce diesel under the right conditions. So we're getting into this concept called energy plantations. But guys, the problem with that is that if you're growing crops and using like trees to make fuels because you don't want to use petrol, that is replacing the big F word. And I better finish that quickly so your minds don't go in different directions. That means food. And that's already happening in Mexico, where the value of corn is more as an energy source than it is as a food. And it gets exported or used within the country. The same is true in Brazil. And people are going hungry because they don't have access to food, because the food is not being grown, like the crop's not being grown for food. And they pay a lot more than we do. So biomass, again, used for direct combustion. It means producing heat to turn a turbine, biofuels, so you convert it to a biofuel, and then you turn a turbine. We can do what's called anaerobic digestion. Okay, that means we can take it and turn it into other materials, particularly something called methane, which is natural gas. We can do a process called pyrolysis, okay, in which we turn biomass into other things, including charcoal. Again, so we can still retain our coal. We can make a charcoal that's very similar to the bituminous and anthracite. If we put in, the problem with making anthracite, you put more energy into it probably than you get out. So whatever. So, but there are processes where we can make a lot of things from what we used to use for petrol. So biomass conversion is just for making energy. It can also be used for making things like plastic, which is what petrol competes with for energy. So, again, this is going to be a very versatile material, and this is going to be probably the future right now for us because it fits with our current turbine or motor and burning fossil fuel infrastructure. We're never going to get away from it. The air pollution issues associated with this, because it's just our comfort zone right now, and it's going to take literally global catastrophic effects of CO2 on the environment to push us away from these things. So I don't condone this that much. I see it as a way of, yes, pushing the energy crisis further forward in time, further away from us. But it's not the answer to carbon dioxide waste. It's not the answer to pollution. These are not clean. They're probably cleaner than petrol because they're chemically more simple, but they're not clean. Hydro, we've talked about. You have to be in the right place at the right time. We're seeing that this is becoming more and more feasible in certain areas, particularly rural areas. We can make better use of their waterways. So this is in a way underexploited. The problem when you do it, though, guys, is you can slow down rivers, redivert rivers. When you build dams, you're flooding areas and drying others out. So we have to be wise about it. But we do see hydroelectric, around the hill country. We see it in a lot of areas. where it's become very feasible. And this just happens to be a damn big dam. And this is out of Japan, but it looks just like Hoover that we see in Nevada. And so a typical dam is you're just having a large body of water move a turbine. This is the same damn turbine you find in a nuclear reactor or a coal power plant, except these are bigger and they're meant to handle the force of flowing water, not steam. So they're a little tougher. And then you have them also hooked up to motors that make, AC current, and they go through power lines. So hydro's nothing unique. It's turning a turbine. The same turbines that are recreated like, a few hundred BC, water wheels, stuff like that, ancient machineries, levers and turbines, wheels. All of these are related machines. Solar can be used in various ways. We could use what's called passive solar. That means the solar energy is used again as a heat source. This is still getting into that old turbine thinking. So if you can collect solar enough to capture to make enough heat, or steam in some cases, you got a power source. So we can directly heat a house. That's what's meant by passive. You just sit there and do nothing. You can heat a wall. They have what are called passive energy walls that are literally a special material that collects the heat, or it can have water in it and heat a room, which we don't need much down by us, except in the winter maybe a couple of days. You could also do what's called active solar. That means you're using the sun to produce electricity in what are called solar panels, solar collectors. And that electricity can then run our housing, including a pump. So two ways that we can use solar. But again, you have to have sunlight. And, and if there's no sunlight, you have to be able to support that by having a little battery. And I'll just draw a little simple battery there. You have to have a battery to store it. Lots of batteries that will get you through the dark periods. So again, here's active solar heating a little more close up. You can see the unit. Okay, and again, it produces electrical current that tends to run things, just like in your regular house. Okay, so electric could, solar generated electricity can either be generated by steam or generated by what are called photoelectric cells, or you can do both. You could have a step-up generator, whatever. But the thing is, you're producing electricity in some way or another if you're not producing heat. And this is sometimes what photovoltaic cells look like. They could look just like regular housing tiles. This is just something holding them down. They could look like the typical solar panel, but guys, usually need a lot of them for an area. This house probably doesn't produce all its electricity for it. And even then, they could easily tap it out and overuse it. So all of our houses would have to look like this. And guys, this is made out of very toxic, very difficult to recycle materials. These produce a lot of pollution and use a lot of resources. So you got to look at the cost benefit of solar. And look at this solar farm. This does not use a large area. And you can't pump this electricity very far too. Unlike a nuclear power plant, you're just not producing the voltage you'll need. Wind energy, again, there's your turbine. AC/DC current goes down a wire, whatever, you're turning a motor. You're using wind. The problem is that the electrical draw on this has to sometimes be stored in a battery. Or if that's going directly to a house can actually seize that motor if this is not turning fast enough to produce electricity for that house. So with these things, you will see brownouts, you will see blackouts, and you have to protect them. And wind farms are very dense. They take up very much like solar power. You need a lot of them to run a moderate city. This is showing the feasibility of solar power. And look at that, even though Oklahoma is windy, and this is the problem with colorblind people, is sometimes we can't tell too many colors apart. So I can't tell you the colors, but I'm assuming this is the good area, but also there's a lot of fair around it. And look, Houston area is only fair. Marginal, not Houston, the Gulf of Mexico is fair. Houston is marginal to not at all. Okay, Florida is marginal, usually coastal areas because you have what are called coastal winds. So actually Galveston does have that ability. Houston does not. We're too far away from the coastal effect. Look at some of this area. Very good, very little superb in the United States, except where no people live. Alaska, whoa, especially the Aleutian Islands and out by Nome. My gosh, been there, done that. Not very empty. And there's, Bayro. Woo, nobody lives there, except people that work there and the natives. So, man, that's terrible. So where the people are in the highest concentrations, the wind energy is only fair to marginal, if that much. Okay, rarely excellent. And that's an issue. And that's why wind is not going to be the major one for us. But it can be a supplement. It doesn't mean you avoid it. It means you can use it to reduce. And we're going to see that's probably going to be the future, is we try to reduce our need on fossil fuels so that we can keep those reserves going and also any future resources going to become a protected reserve. Geothermal, same thing. You have to be in the right location for it. And you use the heat from the earth to steam a turbine, into action. But again, you have to be in volcanic areas. And you see these again in Iceland and a lot of Scandinavian countries. We can actually use this around the Pacific Northwest. But these, because again, particularly San Francisco area with a lot of volcanic activity, but it's not also the greatest place to live because of earthquakes, and earthquakes could also damage this, which is a problem because it uses steam pipes to get that material across, that hot. So last but not least is tidal power, and this actually comes in various forms. And our area is pretty good for this, because we are in a coastal area. And we do have rather vigorous tides at times. So what we usually do is with this type of power, we rely on tides. It means the gravitational pull of the moon and the sun on water that elevates and lowers it, which means it makes the water kind of go back and forth along the shoreline. And we can take this water and divert it through basically turbines that directly produce electricity. Now, there's one group that is actually looking at using a cooling process that takes the warm water, puts it through a system that slowly produces heat that can be used as an energy source too. And so there are tidal units that can heat, but also tidal units that could, mostly turn a turbine. So this is, again, a way that we're never going to run the world this way, but at least we could use it. So the take-home message of this is we're still stuck in a coal, carbon, petrol-based world. Biomass, coal, petrol. We're still going to rely on these, and of course natural gas, which is kind of an outcome of that. But that's our future. The later future, we might start looking at more nuclear and then these alternatives. But a lot of it is still going to require a cutting back of our lifestyle. And maybe not to a Mad Max scenario where we're all living with nothing, fighting for what's left, but hopefully by 2050, we'll get this grasp of what Hans Rosling is hoping, of this whole picture of maintaining our resources over time and being more prudent with it, and also taking more risks with it. So on that note, to ask me, email me any questions. Please read your book about this, and please look at the assignment and watch the videos associated with it. Bye.